I got 8.14.
8.14 moles. All right, thank you. All right, and then it gave us the volume of the solution, but it gave it in milliliters. That's not going to work, right? We need we need that in liters. So we're going to convert that. We need to convert that into all right. So that's going to be, without showing the conversion, we're just going to divide that by 1,000, right? So it'll be 0.667 liters. That's 1 liter is 1,000 milliliters. That's our conversion for that. All right, so then the concentration here, we just run the numbers and get the calculation, and that's it. What do you have? Yeah, thank you, Mary. I just saw your yeah, I just saw.
For this one, I got 12.20.
So it says 12.20 molar, where the big M is for molarity. All right, and let's do we said we would do C. What do we need to do with C? We got a couple of things that we need to do, but how do we, what's our strategy here for C?
All right, you have to convert it into moles again.
Convert it into moles. You can't find concentration without moles and liters. So this is 0.01, 0.001 milligrams. So we're going to have to go from milligrams to grams and then grams to moles. Right, that's the strategy. Everything has to be in moles and liters when you're dealing with concentration. So we know the conversion from milligrams to grams because there's 1,000 milligrams in every gram, right? So it's 0. milligrams times 1 gram over 1 gram over 1,000 milligrams. And then this brings up another topic too, because when we talked about this before, we kind of talked about the fact that when you go from a smaller unit to a larger unit, the number is going to decrease, right? So this number is actually going to decrease and become even smaller. What do you get?
Somebody else gonna have to answer this one because my calculator can't compute it.
Is that right?
Looks right.
Just take my word for it. So really what you're doing whenever you divide by 1,000, that decimal place is going to move 3 times. So 1, 2, 3. So there's going to be the decimal place is going to move, and we end up with this number right here. All right. So this is in grams. Now I need moles, which is what? How do I get the moles? What do I need now? And I have access to it.
The molar mass.
The molar mass or the atomic mass of cadmium. And I can get that from the 2+. Don't let that throw you off because ions and neutral atoms have the same mass, because losing an electron is nothing. They're so small and the mass is so insignificant to the overall mass that it doesn't change anything. So What is the atomic mass of cadmium? I think it's in the same, it's grouped, group 2. Same column with magnesium.
Is it 112.411?
Just say 112.4 grams per mole. So we're going to take that number and divide it by 112.4. And we get, in this case, 8.9 times 10 to the minus 9. That's what I'm getting in my calculator. And this is moles. Now, so we've done the milligrams to grams, grams to moles. And now we can do the concentration. Just divide that by the given volume, which was 0.100 liters. And that's just going to move that decimal place one time. Right, so the concentration here is 8.9 times 10 to the minus 8 molar. All right, any questions about that? So this one took a couple of different manipulations: grams, milligrams to grams, grams to moles, and then taking those moles and then converting it into a concentration by using the volume that was given. All right, we're going to do one more of these, and it's going to be this one right here. And it says a throat spray is 1.4% by mass of phenol. So this is phenol right here. And it says if the solution has a density of 0.9956 grams per milliliter, calculate the molarity of the solution. All right. So this problem is this is another type of concentration, but it is dealing with percent by mass. So there are a couple of things we're going to need to solve this problem, right? So percent by mass, let's talk about that first. The way you calculate this is grams of solute divided by grams of solution times 100. All right. So we also have and we're looking for the molarity, right? Let's get that straight. So we're looking for molarity, which is in what? Moles of solute divided by liters of solution. All right, so that's important. So we know what we need. We need moles of solute. Sorry about that. We need moles of solute, and we also need liters of solution. So let's work on the moles first. That percent by mass, what we want to do is assume 100 grams of solution, right? And so if we assume 100 grams, then 1.4% is the same as saying 1.4 grams. Fix that. Sorry about that. It's the same as saying 1.4 grams of phenol or solute over 100 grams of solution. Right? If we assume that the sample is 100 grams, then we can say that we have 100 grams of solution and we have 1.4 grams of solute. So that solute in this case is phenol. All right. So how do we get from grams of phenol to moles of phenol? Because this is what we are after. Right. We want the moles of solute. We have a way now to find the grams. We got 1.4 grams of solute. We need to convert that into moles. How do we do that? Do we have any information that's present here that we can use to do that calculation or that conversion?
Is it the same as last time? Do we just have to find the molar mass?
Absolutely. We need to find the molar mass of phenol. Yep. So how do we do that? Based on what's given to us. Can we take this and turn it into a molar mass? We got 6 carbons, so that's going to be, let's just round the numbers. So it'll be 12 times 6, 5 hydrogens, so 5 times 1. Well, 6 hydrogens, because the OH, we'll count that one too. So 6 times 1, and then 1 oxygen, so 1 times 16. Are y'all following? All those are just the atomic masses taken straight from the periodic table. So that's 72 and 16, that's 88. And 6 is what? 94 grams per mole. Good. So now we're in the clear. We got everything we need to solve this problem. We have the grams of solute. That's going to be 1.4 grams divided by 94 grams per mole. That's going to give me my moles of solute. So 0.015. Anybody else get that calculation? 0.015?
Yes, sir. I got that too.
All right. So now we got the moles. We need the volume. And the way that we're going to find the volume is by taking the density, which they gave us, and the mass of the solution. Because density is grams over milliliters. And if we take the mass of the solution, we can solve for milliliters. So remember the relationship for density is density mass over volume, right? So V, we can manipulate this. V will be mass over density. And we already assume 100 grams of solution up here. not highlight. That's okay. So we assumed 100 grams of solution. So we're going to put that here. So we're going to say that volume is the mass of the solution, which is 100 grams, divided by the density of the solution, which is 0.9956. grams per milliliter. So we can do that calculation real quick. Anybody got it yet?
I got 100.44.
All right. What's the problem now? You're right. And all of this is right. But in order to get the concentration, what do we need?
Liters, not milliliters.
Liters. Good. All right. So this is 100.44 milliliters, but we need liters. So we're going to just go ahead and convert that. Milliliters are canceled. And then what we're left with, we just divide by 100 is 0.10044 liters. So we found everything we needed. So sometimes you have to derive stuff. It's not just there, right? So from the given information, we use the density and the mass of the solution. Well, we found the mass of the solution. We found the mass of the solute. We found the moles of solute based on that mass and the molar mass of phenol. And we found the volume of the solution using the density and the mass of the solution, right? So all those things, we went through all those steps just to get here to determine the molarity, which is going to be moles over volume. So the moles we said was 0.015 moles. The volume is 0.10044 liters. And that's the molarity. Anybody got it?
I have 0.149.
Okay, good. So the molarity of this solution is 0.149. Great. So this type of problem, like it involves using a lot of different skill sets. But one of the most invaluable skill sets that you're going to develop is the ability to manipulate relationships. Because we took the relationship between density and volume and mass, and we used that to find the volume. We took the relationship between percent by mass, and we assumed that the sample was 100 grams to find the grams of solute. We took the relationship between grams and molar mass to find the moles. And then those are two things those were the two things we needed to find the concentration. So a lot of times we'll have to derive what we need from what we have. That's the whole point. That was the whole point of the exercise. All right, so we're going to switch gears. Unless there are questions about this problem, we're going to switch gears and go ahead and introduce chapter 4. And again, everything is always about manipulating relationships. If you know one relationship, you can figure out some other component of that relationship. If you have the at least if there are 3 things involved, if you have 2, you can find the third. If there are 4 things involved, you got 3 of them, you can find the fourth. Right. So all we have to do is know how to manipulate those relationships to make it work for us. All right. So let's shift gears. Let me change over to a clean sheet of paper. And I'll post that as well as what we talk about now. All right, so we're going to now begin talking about chapter 4. Which is dealing with stoichiometry. All right, that's a fancy word. Thank you, Sierra. I see your answer in the chat. I didn't see it when I was writing it out, but I see it now. Thank you. Stoichiometry is a very fancy word, but really, it's a relationship word, right? So it's just basically the relative amounts and I'm going to abbreviate reaction as RxN. When you see me right there, it's just an abbreviation for reaction. So relative amounts of substances in a reaction. And then we base that on the ratios of those substances, right? So all the stoichiometry is dealing with is the ratios of the different substances that are reacting. That's it. It's a very technical term, but it has a very simple definition, right? We want to when we write out a chemical reaction, everything there is present in some ratio. So that's what the concept of stoichiometry deals with. So for this particular chapter is broken down into 5 sections, and we're going to learn about how to write and balance chemical equations. So that's the first section. So writing and balancing chemical equations. And that's going to involve a lot of other things, right? Because when we write and balance, that's going to give us the stoichiometry. A balanced equation gives us all the information we need about the stoichiometry and the ratios, right? So that's why balancing is so important. We're going to talk about classes of chemical reactions. Right, there are a lot of different types of reactions that we're going to look at. One example that we'll see today is an example of what's called a combustion reaction. But we'll look at double displacement, single displacement, and different types of reactions like that. And then, of course, right, reaction stoichiometry. And then within that concept, we're going to talk about theoretical yield, actual yield, percent yield, limiting reagent, limiting reactant as well as excess reactant. So all of those things are going to be tied up in dealing with stoichiometry. We can derive or calculate all of these things or determine all of these things based on the stoichiometry of a reaction. But the only way to get here and to be able to do any of this is to make sure your reaction is balanced. If it's not balanced, then we're gonna have a problem with doing anything else. And then the last section is dealing with chemical analysis. Right. So all this tied up. It's long. There are a lot of concepts in this chapter, but some of them can be rolled together. Right. Like all the stoichiometry stuff we could talk about while we're writing and balancing equations. And you'll see that with this first example. So one of the things I want to stress is what skill set you should already have by now, right? So you should already be able to do a little bit of rudimentary nomenclature, right? Naming. So when we did those polyatomics and when we looked at the periodic table and looked at the different names for the elements and things like that, you're going to need that because some of the questions are going to give you the name written out and you got to convert that into a formula. You should recognize what your polyatomics are and their charges. And then know how to convert between moles and grams and molar mass. So all these are little skills that we've already been working on developing, right? And so what we want to do in this section is three things, all right, or four things. Number one, we got four goals for this section. And the first goal is to symbolize chemical reactions. So know how to write a reaction. So we want to learn how to symbolize reactions. We want to fluently write chemical equations and balance them. This is the operative word, fluently. So fluently write and balance chemical equations. All right. And then we also want to, and I'm going to say three because two of these goals are very similar. So we want to use stoichiometry to start connecting some of the stuff we already know. So we're going to use stoichiometry with respect to conservation of matter. We're going to see that right away. This is one of the reasons why it's so important to know how to balance. And if you took chemistry in high school, then you probably have at least a decent knowledge about balancing equations, but we're going to kind of ramp that up a little bit. All right. So let's think about this in terms of, so first thing we want to talk about is how to write an equation. So that's the first topic, writing and balancing equations. Right. And so in doing that, we need to be able to go from narrative to symbol. In other words, if they give you the words, you need to be able to turn the words into formulas. And also we're going to talk about different formats like net ionic, where if you have the same ions on both sides, you can cancel them out. Molecular equations, which is the most basic form, and then ionic equations where you have ions reacting with one another. So we're going to talk about that. But when we're talking about a chemical equation, all that simply is it shows atoms or ions reacting together to give new compounds. That's it. And the way that they react on the micro level, I talked to the morning class about this, is they bump into each other. The atoms or the ions collide and bump into each other, and they end up exchanging, ions, or they exchange electrons or whatever, right? But we can think about this in terms of an equation like this, where we take A plus B, right, and we get AB, right? That's one way to illustrate a chemical reaction. We can also think about if we take A, B plus CD, and these are two compounds, and on the other side of the equation, they end up swapping partners, right? That's another type of reaction, right? So this is what we call a chemical equation. It displays two things about what's happening, right? So a chemical equation first thing it's going to display is the identity of the reactants and the products. Right. Second thing is going to display is the relative amounts of each substance. Right. The identity part, that's the nomenclature and the naming. The amounts, that's where we get into balancing and stoichiometry. Right, that's where we get into that balancing and stoichiometry. We do that. When we do that, we determine the relative amounts of things that are present. All right, so we have a basic unbalanced chemical equation. Let's go and do that example. So let's say we have an example of methane, which is CH4 plus O2. And we're going to react that together. We're going to heat it up. So I'm going to put a delta, a Greek uppercase D over the arrow. And from that, I'm going to get CO2 plus water, H2O. Right, so this is a chemical equation. Right, on the left side of the arrow, these are my reactants. Right, on the right side of the arrow, these are my products. Sometimes you'll see me abbreviate this as PDT. Right, or reactants will be just R. All right, so my reactants and my products, the reactants are the two chemicals or molecules or atoms that are coming together to form some new compounds, right? So if you notice on the other side of the arrow, that's CO2 and H2O are totally different. That's not the same thing that's on the reactant side, right? So that plus sign right there, this is telling me that a reaction is taking place. right? So it's this thing plus this thing, and they're going to come together, collide at really high velocities and under certain conditions, and boom, we're going to get something new on the other side. All right. And then the plus over here, this tells me that I have multiple products. Right. So the plus on the left side says that a reaction is happening. Plus on the right side says I have multiple products. And then over the arrow, right, you see I have this delta, right? These, when you write a reaction out, so you write it out with the conditions over the arrow. So these are my conditions. So it could be heat, or temperature, time. It can be light, whatever. Like light, sometimes you add like UV light, you do a reaction under UV radiation, so on and so forth. So you want to put your conditions over the arrow, or sometimes underneath the arrow. And then on the right side, products, left side, reactants. Now we got a problem here, because if we look at this reaction, how many carbons are on each side? How many carbons on each side?
One.
Just one, right? How many hydrogens?
4 and 2.
Got 4 on this side, 2 on this side. All right, good. And then oxygen, what do I have? 2 on this side and 3 on the other side. Is that right? I got 2 here and 1 here, for a total of 3. Yes or no?
Yes, sir.
All right. So that's a problem, because when we learned about Dalton's atomic theory, one of the things that we learned about is indivisibility, right? We also learned about the law of conservation of matter. So you can't destroy matter or create matter. But if you leave this like this, what it looks like is you've created one extra oxygen atom and you destroyed 2 hydrogen atoms. And we know that that didn't happen. So the way that you fix that is to balance the equation, right? Because you have to have the same number of atoms on each side for any given reaction. So let me put that in here. All right, got to have the same number of atoms on both sides. So the way I'm just going to put this in because we're running short on time, but on tomorrow we'll discuss it in more detail, like why we did what we did. But let me go ahead and I'll put in the coefficients. So this is CH4 plus 2 O2, and that's going to give me CO2 plus 2 H2O. Now, how many carbons do I have on each side? What did I use for carbon? How many carbons? Is it still one?
Yes.
Now, how many hydrogens do I have on both sides? Now, I got 4 on this side. And what about on this side? So now you can see here, this 2, this coefficient, I'm gonna run it through, and it's gonna be 2 times the H2 and 2 times oxygen, right? So now I have 4 hydrogens on that side. And then oxygen wise, what do I have on this side? Because I'm going to multiply that
4.
4. Good. And then on the other side, how many do I have? I have 2 here. What did I use for oxygen? I think it was green. I got 2 here. And then this 2 multiplied by that, it's going to be 2 there for a total of 4. Is that right? Anybody not seeing that? So now this is what we call a balanced equation. And the numbers that are in front of those molecules or atoms, I should use a different color than that. Those are what we call, it's too close to the carbon. So these numbers right here, these are what we call coefficients. So whenever we're balancing, that's how we balance an equation, using coefficients or numbers to even out the number of atoms on each side, right? And those coefficients give us all of our stoichiometric information about the ratios between the molecules. We can figure out all those relationships from the stoichiometric coefficients. All right, so we got to stop here. We'll pick this up on Thursday. We won't have class Friday, but we're going to keep pushing with this balancing and writing equations. We're going to keep pushing with that on Thursday. All right. Any questions about anything?
I got a question.
Go ahead.